Yes.
Are you posting a sample of?
Nope. You know how hard these things are to make?
Past exam.
The notion of making, but like, you know the library has exams from like the past 4 years. Those are your samples, so take those. The final exam this year is going to be like those ones. Because there's a rule that in the mathematics department, the professors have to evaluate the exam. We don't trust our TA, which means we're going to have to introduce some multiple choice, right? Otherwise, me and Mike will be marking for days, right? So it's going to be multiple choice and full answer. It's not going to be like your midterms. It's going to be more classically like the past
Like
year's
Scantron stuff?
So, well, you guys know how to fill up Scantrons. You're the life science students, so you should be experts at filling out Scantrons.
Yeah.
That being said, I may try to find, there's like another app that we have where it's like, we give you one of the sheets on the test you fill out, and I can like evaluate it with my cell phone, but I may not get access to that. Anyways, you can fill out Scantrons, yes?
Yes.
Okay. The twist may be for our test is that I'll give you, have you guys ever had a test where you're penalized for answering wrong? Okay, it's going to be like that. Except I'm not going to penalize you for answering wrong. I'm going to do something which is equivalent to penalizing you for answering wrong. I'll probably give you 2 marks for a correct answer, 0 marks for incorrect answer. But I think I'll always have a bubble that says pass, and I'll give you 1 mark for passing.
So you can get a 50 if you just answered pass for all of them?
Yes, but that's not going to be the best.
No, probably not what you want.
That's probably not what you want, right? It's not going to get you across over a threat. I'm basically discouraging everyone from guessing, right? So if you're like, I am truly guessing on this question, you can take 1 mark, right?
Fair play.
Maybe I should make it 0.25 marks. That would jive more. Well, because that's your expected guess. Well, yeah, now you want it to be. I'll have to think about this.
Numbers are better.
Well, because you could leave all the true false blank and get.
But like, I have a problem. But I don't think anyone would. I have a problem with model numbers.
Shh. Yes, please. Yes. Yeah. I'm not going to leave you anything for leaving full solution things blank. But that being said, when you don't know how to solve something, writing gibberish isn't going to get you anything, right? You're always trying to explain to us that you do understand something about the math. So it's better to even write, like, I know you guys didn't like this whole like stuck framework, but that's going to get you partial marks. If you can say, I can't continue for this reason. Or I know, like suppose like you're checking over your exam and you realize in the last minute that your answer is wrong. Instead of trying to fix it, I would write on my test paper, yeah, I know this is wrong. Here, this is a mistake. I don't have time to fix it. You would be surprised how often you'll get marks for that. I should have brought it, but I got full marks once on a test where I like outright gave up on the question. And I wrote, this has something to do with this. Got the test back, 5 out of 5, perfect. Like, that was exactly the answer that they were expecting. So sometimes we think that we don't have the answer because we're answering some different question that we think that the professor is asking. Right? A lot of you often just overcomplicate things because you say, this can't possibly be the answer. And it's like, well, it was. Right? So if you're trying to go for partial marks, try to do it in the right way. Right? Okay, so today we're into now the last chapter of the book, which can be qualified as somehow really the first real type of mathematics that you're going to learn. So we'll see how it goes. So today we're going to start talking about sequences. So consider this. 1, 2, 4, thank you, 16, 32, and so on. This is an infinite sequence. Of powers of 2. Yeah? So we've dealt with this a little bit when we were talking about the sum notation, but now we're going to talk a little bit about it more strictly. So what we can do is designate the nth term of this sequence by an. Then we can say that an is what in this case? And remember, we've got to be careful with bounds. So usually we have to specify if our n is going to start counting from 0 or start counting from 1. So I'll usually just say something like this. Right? We're going to define an for n greater than equal to 0, or I'll say for n greater than or equal to 1. But can someone give me the generalized pattern for this thing? So that a0 gives 1, a1 gives 2, a2 gives 4. Yes?
2 to the n.
Indeed. 2 to the n. So does everyone see here that a naught would be 2 to the 0, which is 1. a1 would be 2 to the 1, which is 2. a2 would be 2 to the 2, which is 4, and so on. Okay, so in general, a real sequence is denoted like this. Right, so this denotes a real sequence where the nth term of the sequence is given by an. Like you should also note that it doesn't have to be a, right? Like bn is also a sequence, cn is a sequence, xn is a sequence. Maybe we wouldn't choose that because x's are sort of utilized for other things, but don't get stuck thinking that this is the only one that we can choose. But the point is, if you see me write this an with brackets around it, you're to assume or treat this like a sequence of numbers. Okay, so let's see if you're able to detect patterns. So I'm going to give you maybe 2 patterns here, or maybe even 1. Let's see. Okay, so here's a pattern. Let's say that it's 1 over 9, 2 over 12, 4 over 15, 8 over 18, 32 over 21. So I'd like to know what the nth term of the sequence looks like. And for 2, give this one a try. This one's a little bit harder. 5 over 1, 8 over 2, 11 over 6, 17 over 120. I want to know what the nth term is here. So work on that for a bit while I write down the boards. See if you can guess. You're going to have to guess. I'm going to have to get good at guessing because there is no strategy for figuring these things out. I'm going to erase the left half of the board. Is that okay? Okay. Who has some water? Anyone have water? Is that water or cup?
I have water.
Water?
Why?
It's not wiping the board down very effectively.
What is that? How you do it?
Yeah, water helps quite a bit.
Oh. Well, you know.
Thank you for that. Tough, eh? Sometimes they're not obvious. So what do you think a good strategy here would be? So this is why I always want you guys to factor stuff. That's where the patterns become obvious, right? Not when you multiply things together, but when you unmultiply things, when you factor everything. So let's look at the first one. Usually, we'll look at these things. Maybe there's a pattern in the numerator, and maybe there's a different one for the denominator. So what do we see in the numerator? Yeah, like it's 1. Yeah, it looks like we have some type of powers of 2, right? It looks like we have 2 to the 1, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. Okay, so what about the numerators? What do we see?
Starts at 9.
Starts at 9, 9, 12. Okay, so we have 9, and then 9 plus 3, and then 9 plus 3 plus 3, 9 plus 3 times 3, and then 9 plus 4 times 3. Yes, miss?
Question. Wouldn't 2 to the 4 be 16?
2 to the 4. 1, 2, 4, 8. Oh! Yeah, maybe I wrote down the pattern wrong. 2 to the 4. You're correct, sorry. This would be 2 to the 5. This should have been this should have been 16. Okay, so now you all have an excuse. Now you should all be like, oh, well, I would have got that. Yeah.
But in a pattern, you don't need to expect like all the numbers to be in the same order. You can say that like you can just give it a random number of random numbers, and then we have to decide whether or not that's in the exact same order that we put.
They can't be random. How would I say that? We learned the other week that randomness is not to be trifled with. I can't just say let a and be a random number. You have to say let this be a distribution. Let x be a sample from this distribution. So, given a finite sequence of numbers, there is definitely a pattern that goes through them. I can prove that, right? So you'll always find some pattern for those numbers. It may be very complicated, but it exists. Yeah.
But what if like rather than saying 16 over 21, you did put 32 over?
We could find a pattern that would satisfy it.
In that sense,
Yeah.
as long as there's pattern, it doesn't need to. Sorry, my question I guess I stated wrong then. So rather than having the nth number be in order, it can be any number. That nth term can be any number. So we can have 2 over 12, 1 over 9.
Okay, so you give me a set of, let's say, random numbers, right? Provided that those random numbers are, like you just give me 10 of them, you eventually stop. I can find a pattern that goes through them. It may be a crazy complicated pattern, but it definitely exists. Actually, it's worse than that. There's an infinite amount of patterns that go through every finite set of sequences. So these things aren't even unique. There's a lot of like stuff that I'm hiding. But suffice it to say, we'll never ask you to find a pattern of something which is deeply complicated. Like I could create a pattern where it's like integrate this super difficult functions from 0 to x, and that's going to, let's call that the nth number. Like you'll never have a chance at guessing something like that. We're limiting it to these like sort of simpler cases, suffice to say. Does that sort of clear things up? Okay. What was the pattern here then? Yeah.
2 to the n over 9 plus 3n.
So it's going to be 2 to the n over 9 plus 3n, I think. Let's just strive for the first. You should always strive. So for 0, you get 1 over 9. For 1, you get 2 over 12. For 2, you get 4 over 9 plus 6. Okay, so this does seem to work. What about the next one? Anyone have any ideas there? Well, look at this. How do you get from 5 to 8? How do you get from 8 to 11? How do you get from 11 to 17? How do you get from 7? Oh.
We need another term, maybe?
Did we need another term?
Because then if it was 9 for the next term, it would make sense.
I also wrote this down wrong.
No.
Good.
That's what I was like.
So now all of you guys should be like, yeah, that's why we couldn't get it.
That's my
That's what happens when I'm rushing, right? So this should have been 5 over 1, 8 over 2, 11 over 6, 14 over 24, 17 over 120.
24.
All right, well, anyways, I'll just give you the general pattern. So here,
No, I totally see it.
yeah, there's a 3, then a 3, then a 3, then a 3. But what's the pattern on the bottom? That's the thing I suspect you.
Times 2 times 3 times 4 times. Is that true? No.
Which?
I don't know.
So anyone? So
Yeah, wrong now.
what's the pattern on the bottom here?
No, it does make sense. It would be 1, or the term. Or okay, so let's just say 1 times 2
Okay, so
Be 2.
this one is going to be 1.
times 2.
This one is going to be 1 times 2. What's this one?
This would be 2 times 3.
1 times 2 times 3. What about this one?
And then times 4, right?
1 times 2 times 3 times 4.
And
What about this one? 1 times 2 times 3 times 4 times 5.
Sure, yeah.
Okay, so actually the general pattern is for the nth term, I need a 5 over 1. So I'm going to say n factorial. So here we have to start from 1. And then how do I get a 5? So that's going to be 2 plus 3 times I. So let's try the first few. So for 0,
What's the explanation?
It's factorial, so it's like 5 times 3 times.
explanation, it's just that what the pattern is,
That's what a factorial is.
right? It's just all the numbers multiplied from in a ladder.
Like 2 factorial is 2 times.
Okay, so if I put in 1 here, I get 5 over 1. If I put in 2, I get 8 over 2. If I put in 3, I get 11 over 6, and so on. So that seems to work. So you guys are going to have to gain some
Is that 3
skill in getting these patterns.
Why is it I?
What?
Why is it 3 I's? Or is
Oh,
it-
sorry, 3n,
Yeah,
3n,
okay.
sorry.
And then n.
Yeah, okay. That's our warm-up. Okay, we may have to be clever, though. Like, I'll show you another example where things are even a little bit more complicated than that. So if I let dn equal this, a half plus a sixth, and I can even tell you what the end result is. Okay, so this is a sequence where the I, did you knock something? Yeah.
No.
What's up?
Did you solve the bottom? Like it's 2 plus 3 to n over what is that?
N factorial.
Oh, that's the factorial.
Yeah.
What does that mean? That means it's
Shh.
like.
What do you mean I don't understand what you mean I solved. Well, tell me. Yeah, I'm confused as well.
What does n factorial mean?
N factorial. Oh, you guys don't know what the factorial function is?
No.
Oh, it's easy.
Well, when you said it, yeah.
Right, 4 factorial is just.
So many O's.
It's just, yeah, just multiply. I can give you the recursive definition. N factorial is n times
You already told me the
n minus 1 factorial, and 0 factorial is 1. This is how you do it, essentially.
Do you have to write n greater than 1?
Well, does it work for 0?
No, but like for the rest of them you didn't. Is it just for this one?
Well, we usually have to specify if the first index is 0 or 1. Right? This wouldn't work for the first index being 0. I have to address the denominator. You get to choose, right? Sometimes 0 will be the one that you want because it will have nice properties, and sometimes you want to start at 1 because the 0 is obnoxious. Right? Just keep this in mind. You have to be very careful about the first index being 0 or being 1. Okay, so here's a little bit of a different type of sequence. The sequence itself is not given by this nth pattern. It's given by the sum up to that. All right, so this is something called a partial sum. So can we work out some of the first few terms here? So what's d of 0?
0.
Well, I guess we can't do it because it's saying we got to go up to here. All right, so we should even consider it. Right, so this means that the index starts from 1, right, because it's not defined for 0. Okay, so what about 1? Okay, we got to add everything from a half up to 1 over a half, right? So that's just going to be a half. So d2 is going to be what? 1 half plus 1 over 2 times 3, which is 6, which is 4 sixths, which is 2 thirds. Can you give me the next one, d3? Yeah, so like it's going to be this, like the last thing, plus the next thing, which is 3, so it's plus a 12th. So this is going to be 8 twelfths, 9 twelfths, 3 quarters.
Do we subtract them to find a distance? Or
There are differences up
okay,
there?
but d1, right?
Yeah?
So you plug in 1.
Yes.
You're saying what's between half and 1?
No, I'm saying we add up all of these terms until we hit this.
Oh, which will.
So the first one is just a half, right? It does, like we don't even have this for 1. This is the nth one.
So the half over there.
It's like this, right? Like a half plus a sixth plus, hold on, a 12th plus for what, a quarter, a 20th, one more, a 30th, and so on. right?
Yeah.
The first term is this. This is D1. The second term is this. This is D2.
Oh.
The next term is this. This is D3. Right? You understand? This is called a partial sum. We'll talk about this a little bit more. But I can define a sequence of numbers in whatever manner I want. Right? So, okay, so the question is now, what is the limit as n goes to infinity of this sequence of partial sums? Can any of you sort of work it out? Okay, so it's just to show you that we're going to have to be very tricky when it comes to these type of problems. What have we learned about partial fractions? How can I break this up?
We can do 1 over n minus 1 over n
A
plus
over n?
Yeah, it's 1 over n. I believe it's minus 1 over n plus 1. But you're on the right track, right? If you do partial fraction expansion on this, you're going to end up with this.
Okay.
Right? It's n plus 1 minus n. Right? 1 over n plus 1. Okay, so that means I'm actually adding something a little bit different. So I could rewrite this as what? This is going to, I need more room. Okay, so dn then can be written like what? Instead of writing these at every step, I'm going to write this at every step. Right? So the first one is going to be what? 1 over 1 minus a half plus 1/2 minus a third plus 1/3 minus a quarter all the way on till the end, right? 1 over n minus 1 over n plus 1. Does anyone notice anything about this sequence?
Yeah.
So you're telling me that you see cancellations here, right? Look, minus a half plus a half. Minus a third plus a third. Minus a quarter, it's going to cancel that next thing, and this 1 over n is going to be canceled from the thing there. What we're left with is 1 minus 1 over n plus 1. Right, that's going to be the nth term of this sequence. We have this is much easier now to work with. Can we confirm that this works for D3? So what was D3? D3 ended up being 3/4. My new rule says it's going to be 1 minus a quarter. Yeah, that seems to work. Moreover, can we now determine what the limit of this sequence is?
It's 1.
Yeah, what's the limit of this as we push n to infinity? Well, yeah, 1. Okay. Isn't that interesting? That if you add up all of these numbers, a half plus a sixth and so on, you would get 1 in the limit.
So which equation do we use?
We didn't have any equation. We used reasoning.
1 minus 1 over
What equation did we use for this?
n times n plus 1.
What equation?
Like 1. Well,
This is not an equation. This is me telling you, I'm defining a sequence like this.
yeah.
Okay, now I'm asking you the question, what is the limit of this sequence?
Oh.
There are no equations that we utilized here. All we utilized was sort of mathematical ingenuity. Sorry.
Why don't you split it up like that?
Yeah.
You could've
Why
just-
did I split it up like this?
You can do 1 over n times 1 over n.
I could have done it an infinite amount of ways, but this way allowed me to get this cancellation. I did it this way because it worked.
So it's just intuition?
Intuition. You guys are going to hate it. Right? You got to gain some practice. It's just like integration all over again. I can't tell you how to solve these problems ahead of time. There is no generalized method. I'm going to teach you how to attack some, like in fact it will normally be the case that no limit exists, that you can't find it. When we start talking about sums, it is normally the case that there is no closed form for the sums. We're going to have all the same problems again. There's going to be a limited amount of problems that we're actually able to solve, and I'm going to show you all of them. I'll categorize them for you. Yeah.
That one's general. Wait, so.
How is this general? This is a very specific problem.
1 over n times n plus 1 is only specific to that.
To this problem, so how is it general? It's specialized. Yeah, it's the opposite of general.
So that, like, otherwise we just have to
well, let's do more examples, right? Don't get too wrapped up in this because we have a lot more to go. Okay, so I have to give you some theorems. And there's another type of, there's a different notation that's sometimes utilized here, although I do want you guys to avoid it. Okay, so if I say we have AN and BN sequences, and we know that, and here's the, okay, so here's one notation that I can say. I can say the limit of n goes to infinity of AN is equal to A. But it's often the case that we write that there's two alternatives. We can say AN goes to A. That's what that arrow means. I can also say AN goes to A, and I just write n goes to infinity above that. Right? So there are at least two other ways of writing these sequences. The analysts prefer this. Right? This is more of a calculus thing. Okay, so if we have, here's a theorem. I'm going to have this. I'm also going to have that Bn tends to B. Then it is the case that we have all of these nice limiting rules. We have the limit of n goes to infinity of AN plus BN is equal to A plus B. Right? That is to say that like the limits distribute across the sum. You also have subtraction. You also have the limit of n goes to infinity of k for a constant times AN is equal to k times A. And we also have that the limit of n goes to infinity of the product of two sequences is equal to the product of the sequences. And you also have the division version of this, except b in that case can't be 0. We're usually prohibited from dividing by 0. All right, so most of this sequence stuff is going to be very similar to that of limits. So it's a good thing that we sort of end here because we get to have like a little refresher about limits. That being said, who can remind me what the sandwich theorem is? Oh, okay, squeeze theorem. Even in just English, can you describe me what this meant? Why did we use this? What was the sandwich theorem for?
If I can't figure out the limit of one function, I can see two functions that make that function.
All right, any other tries?
I give up.
Remember, we're always trying to find the limiting behavior of some function, right? Which are just like these sequences, except they have all the holes filled in. Sometimes that behavior was really hard to view, right? Things can go crazy. So we had this tool for trapping the limit in between other two limits that we could calculate. And we said, look, this limit I don't know, but I know this limit, and I know this limit, and the limit I want to find is trapped. So we've squeezed it between two limits that we know. It just turns out we have the same type of behavior for sequences. This shouldn't be a surprise. So remember this term eventually, so just bear with me. So if there is a natural number such that AN is less than BN is less than CN, right? This is the eventually clause. I'm just saying it's eventually the case that this is true. Then I can apply a limit over this essentially. The limit of n goes to infinity of AN is less than or equal to the limit of n goes to infinity of BN is less than or equal to the limit of n goes to infinity of CN. Right? So now the trick is to try to trap the sequence whose limit you want to deduce in between two sequences whose limit you know. So let me try to give you a little problem. I think I can fit it in here. So this is going to be our next example. So why don't you try to work it out? I want to define the sequence AN is equal to sine of n over n. And I want you to tell me what the limiting behavior of this is while I wipe down the boards. Can I wipe down this half as well? All right. By the way, this factorial function is super important, right? You're gonna need it in like the next couple sections, so learn it, please. Okay? We talked about it a bunch of times. Like it's definitely going to be a symbol that can show up on your exam. Is anyone attempting it?
I'm trying to.
Add like sin x over x or sin x.
We have all of these theorems for functions.
Oh, that doesn't apply.
These are well, not. We have to establish a framework for saying so, and we will. This is different than a function. This is like the finite. That's finite. This is the countable points, right? Sine 1 over 1, sine 2 over 2, sine 3 over 3. We don't have like this isn't a function, right? So we can't use L'Hopital's rule at the moment, for example. Right?
You plug into your calculator. Just to be sure.
We finished with Power series and Taylor series, yeah,
Still do it on test.
which are very, very important.
It's like 3 things.
Okay, let me just remind you of something.
What was the first time we used the calculator?
Exam, 3 weeks. You guys are way too happy.
Yeah. Maybe we're delirious.
Okay, so remember when I asked, like whenever we give you a sandwich question and we give you a trig in it, that is a strong hint of where you should start. And we've done this heaps of times. So what's the starting point if you see a trig in your question?
We can say that sin x is good.
That's a great starting point, right? We always say something like sine of n, gotta move that a little bit, sine of n is less than or equal to 1 and greater than or equal to minus 1. This is always a great starting point when you're given these trig functions. Now, what do I have to multiply this by in order to get the thing that I have up there? Okay, is it safe to multiply by 1 over n? By which I mean this is an inequality. We have to be careful now, right? If we multiply by negative numbers, we have to change the signs, or the inequality symbols. Okay, so what are my n's in this case?
What are your n's?
Yeah, what n's? Can I start from 0 or do I start from 1? For this one. It's easy to establish. Is there an a naught? Is there an a 0? No. Okay.
Is it from 0 to 2 pi?
No, this isn't a function, right? This is a sequence. And the nth term of the sequence is given by that rule.
Oh,
Right? So a1 is sine 1 over 1. A2 is sine 2 over 2.
okay. All right.
Does people beyond the front row understand that? Okay. Okay. Anyways, so what are my n's in this case, right? 1, 2, 3, 4, 5. Are they positive? Yes. Is it safe to then multiply by 1 over n?
Why can't it be negative though?
Because we don't. I'm not indexing backwards. I guess it could be negative, but in this case, it's not.
Okay.
Right? We can always, even if you wanted to negative index, I could shift the indexes to be positive. Right? But don't overcomplicate things. But I guess that's technically an appropriate question. Okay, so I'm going to multiply by 1 over n everything, which means I get 1 over n less than or equal to sine n over n is less than or equal to 1 over n. Okay, so now what do we observe in the limiting behavior?
Well, as it approaches infinity, it's going to be negative infinity and positive infinity.
What?
No, they have to be the same.
Approach is 0.
This approaches 0 if I push n to infinity.
Oh,
If I push n to infinity, you get 0. That, well, the limit of n goes to infinity of sine n over n, and 0. Okay, so now what can I conclude?
you can conclude that the limit.
Yeah, that the limit of that sequence as n goes to infinity is 0. Okay, but don't treat these as functions, because they're not. I'm using a function to define the nth member of a list. Okay, so here's another theorem, and you don't really have to remember these. We just need to establish. I want to use all the calculus that we have developed, like L'Hopital's rule, and all of these intuitions that we've gained about real valued functions. So I need something that says, if I have a function that goes through all of my points, then I can use that function and get the same limit on that function as I would by taking the limit on the sequence. So I'm going to write you down a statement, and we'll sort of try and decompact it. So we have this, if an is a real sequence, and we have that an limits to L in its limit, we have that f is a continuous function, at L, and f an is defined. And what we have basically is, insteed of having this, right, or I have this sequence essentially is equal to a function whose graph, how do I say this? Like we have the graph of f is equal to 1, a1, 2, a2, 3, a3, and so on. Right? So I basically, instead of having a rule like an, I have a function which reports it. So like that actually would qualify for this case. Right? Because I have a function, sine n over n, that is giving me what the nth point in the sequence is. Right? So we just have a function that at 1 gives us a1, at 2 gives us a2. To visualize this, it's like we could draw each of these sequences, right? If I had 1, 2, 3, 4, 5, 6, and so on, this would now be our ends. And then I could just draw what they are, which are now something like this. And the theorem over there says if I can find a function that goes through all of these points, right, if this is a function f, then the limit as n goes to infinity of fn is an. Right, so this is basically saying, look, if instead of having a sequence of discrete points, you have a function which is continuous that happens to go through all of the points at the integer places on the real line, then we can just take limits on that function, utilizing all of the old calculus that we had. It'll be more obvious in its application. And then after this, I have to give you one more theorem which is going to allow us to use L'Hopital's rule. But let's try it on an example. Yeah, you got to get some work in with these sequences in series. It has the troubling property of looking easy but being hard. Okay, so here's an example. Suppose we have a sequence an whose nth term is given by n plus 1 over n to the half. And I want to ask the question, what does an trend to? How would I do this? Well, we want to utilize that theorem. So can you give me a function that at f at 1 gives this, at f of 2 gives this? Okay, well, maybe this is a little bit tough. So how we do this is like this. I'll show you once, then maybe it'll be clear. So I don't really know how to take the limit of this, because if that's square root. Can you take the limit of the thing inside? Okay, so let's do that instead. Let me define Bn to be the sequence n plus 1 over n. Let me define the function f of x to be the square root of x. What that theorem actually tells us is that the limit of n goes to infinity of an is equal to the limit of n goes to infinity of f at bn. Could everyone see that? Right? And that theorem tells us that we can move this limit inside. right? So this is going to be equal to f of the limit of n goes to infinity of bn. Okay, so can we finish this now? What is the limit of n goes to infinity of this? 1. Right? As n grows huge, this 1 is irrelevant. So you end up getting 1. Right? So this is really f of 1, which is what? 1.
We can just guess one.
So that's how you do it, right? You sort of like look for a sequence that you do know the limit of, take it out, right? And then apply a function. Well, what's up?
I'm just gonna keep having this confused face.
Well, like, can I help you not be confused? I think the confusion is usually from treating these like functions. They're not functions, right? What we're working with is an ordered list of numbers, which can repeat, right? And we have access to the last, to the pattern or not.
Could we have done this in a different way?
Huh?
Could we have done this in a different way?
Could we have done this in a different way? Sure, you could have done it experimentally, I guess.
No, I mean like when answering these questions, would there be multiple answers? Or?
Oh yeah, usually. Yeah, you could guess at the pattern. Yeah.
Could you go through it again? I didn't understand that.
Well, can you isolate it? Okay, because I didn't write very much, right?
Like, okay, so you're trying to find.
I'm trying to find the limit of this sequence.
Yeah, well, as n approaches infinity,
Yes.
what is that going to equal?
1.
And that's saying that,
Yes.
like,
So if you take the limit of the left side, right?
What left
Limit
of
the
this?
left side, yeah.
I mean, that's-
It equals the limit of f of the right side?
I'm saying like if we can regard this sequence as being this simpler sequence and applying a function to it. And we have a theorem that says that we're allowed to do this. It won't affect the limit. Right? Basically, it's all like the whole strategy is codified here. I don't know how to find the limit of an. I do know that this limit is equal to this one, and that I have a theorem which allows me to carry this limit inside, right? So instead of finding the limiting behavior of an, this harder thing, I'm finding the limiting behavior of the argument, which is easy, and then applying the function afterwards. Yeah.
and bn in this case is n plus 1 over n.
Yeah.
And you got that from,
Just pull it out of there.
but what about the exponent?
I dropped it because, well, if we could answer that question originally, we wouldn't have to do anything.
It doesn't matter though,
Yeah.
because it approaches infinity though.
You could have taken this limit by looking at it. I don't think this is obvious that this goes to 1. Right?
Okay. I mean, I'm just trying to figure out why you chose n plus 1 over n.
Because that's the thing inside here. Anyways, let's move on or I'm going to run out of time. Right.
But why does the exponent matter? Like at all? Why does an exponent there? Like why is?
Do you not see here?
I'm sorry.
Here. Like, that's where the exponent went.
So you square rooted the 1. When you found the limit of n plus 1 over n, you square
Yeah,
rooted
here.
the
Yeah, the f of 1, this f. Yeah.
So f of 1, okay, is 1.
Yeah.
Okay.
Like, basically, okay, let me try to explain it like this.
So
Uh,
you let a function equal.
Let me try to explain it. Let me try to explain it backwards.
Sure.
Right? Suppose we know the limiting behavior of some sequence. Right? I can always define a new sequence like this. Bn is equal to, you pick a function,
Whatever.
and I'm just going to evaluate your function at every member of this other sequence. And now I'm going to ask you to find the limit of this.
Okay, and
But
bn
suppose f is crazy complicated.
Sure.
Then how are you going to do it? Right? I'm saying, well, look, we actually can do this.
And that's just taking the limit of the thing that's on the inside.
Yeah, but the problem is, you're starting here and having to undo it.
Okay.
Right? You have to sort of see, I'm like giving you a sequence, and you have to see it as some other sequence being put through some function evaluation in order to exploit this.
Okay. All right. That makes sense.
So like you asked, why did I pick it? I said, I picked it because it ended up working,
Because it's
right?
convenient.
Maybe I tried to do 10 other things that didn't work ahead of time, right? But you could see how I could always construct an arbitrarily complicated sequence by just applying, if you give me a sequence 1, 2, 3, 4, 5, 6, and I like send it through the Heaviside function or something like that, Actually, that would be easy. I send it through the Bessel function, right? Something they don't even know, right? But that's the technique in a nutshell, right? You have to sort of backwards engineer it.
This is like the integration of limits.
No, don't. This has nothing to do with calculus.
This
right?
is the integration in quotations of limits.
Okay, so let's try another one. Okay, so here's a good example.
Backwards of limits, right? Or are we? Maybe not at all.
Okay, so I want to know. Here's a limit. Whoops.
More practice.
I have to give you a theorem again. Okay, so here's another theorem.
When you do the first couple of questions, then you start it. Okay, then.
Okay, so if again we have if an is a sequence and fx is a real valued function, and we have that an is equal to f of n, then we have that the limit of x goes to infinity of f of x is equal to the limit of n goes to infinity of a of n. So this is a little bit different than the last theorem. Right? This says if I can find a function that passes through all the same points that my sequence does, that I can just do a limit on the function. And because we can do a limit on the function rather than doing a limit on the sequence, we can use things like L'Hopital's rule. Like basically, I'm introducing this theorem in order to use L'Hopital's rule. You can forget it. The theorems, like we're never going to ask you to restate them. It's just technically speaking, we have to introduce some type of mechanism to get us from sequences back to the world of functions. Okay, so if I asked now, okay, if we have this example, I want to know the behavior. So here's my nth term, and it's ln n over n. Right? So the first thing you have to do is find me a function x, right, which has this property. So we need to find x, or find f of x, such that f of 1 is a1, f of 2 is a2, and so on. Can you do that for me? It's very obvious in this case. Right? My nth number in my sequence is ln n over n. So what function do I have that has this property?
Just
Can you do ln x over x?
ln x over x.
Yeah, ln x over x. So choose.
Actually,
Yeah, don't overcomplicate it. So we're going to choose this function, basically. We just noticed that, oh, look, right? Instead of doing ln n over n, right, we actually are going through all of the points of the true function ln x over x. So this theorem is basically telling us that the limit as an goes to the limit of an as n goes to infinity is going to be the same as the limit of f of x as x goes to infinity. So what is the limit as x goes to infinity of ln x over x? Right, so we have correctly identified that that goes to infinity, that goes to infinity. That's the infinity over infinity indeterminable form. Or, yeah, so we can use L'Hopital's rule, which means what? We do quotient rule, right? No.
Just the right to top of the box.
Yeah.
Why did you say that?
Well, I just want to see where we're at. Yeah, we have to take the derivative of the numerator and the derivative of the denominator. We are not, in fact, taking the derivative of this. We do not use quotient. Right, so this is going to be 1 over x over 1, which goes to what? 0. Okay, and because of that theorem, this implies that an goes to 0. You just need some practice, right? As usual. It's just a different way of thinking. Like you're so used to working with functions, and now we're working with lists of numbers. Right? It's going to take a little bit of a shift in thinking. It's like we're now dealing with functions whose domains are always the integers. You can think about it like that. Right? Do you guys have any past experience with like computer programming in high school or anything?
Hell no.
Oh, okay, that's why.
Hell no.
Because these are basically arrays from computer science.
Alright.
Computer scientists are totally fine with this. Because this is just basically a mathematical version of what they've been doing with the computer. You guys should take some computer programming courses. It's a fairly important skill set to have nowadays.
What was the CS unit instead of this power?
CS unit.
Oh my god.
Okay, so here are some useful identities.
Casually continued.
Continues on.
We have to teach you sequences and series and power series and Taylor series because all of you will probably have to learn statistics somehow. And you'll find we're talking about probability density functions. At least some of you are with me for that. One of the most important probability density functions is called the normal distribution. I'm sure you've heard of this. The problem, okay, so how do we pull off probabilities for probability density functions? You have to integrate them, right, over intervals. We don't have an integral for the normal distribution. One of the most important distributions in statistics is not integrable. Don't you find that surprising? Wouldn't you think that one of us would have been able to do it by now? Thereby, the only recourse you have when taking integrals over the normal distribution is to use approximations. Everything in science, in statistics, these will always come down to sequences and sums. And sums are tricky bitches. They don't behave as you would expect. Right? The same way that the other day I showed you that with an infinite perimeter, you can bound a finite area. We're going to learn we can sum up an infinite amount of numbers to get something finite, which is strange. Okay? So these techniques may seem useless, but they are in fact the only tools we have for tackling science. So how's that? Yeah. We could go to the math world, be like, well, let's just assume we can integrate it and continue, which is what mathematicians would do. But that's very theoretical. We'd have no attachment to the real world. Okay, anyways, let's see how many of these you remember. What does ln n over n limit to? Right? In each of these cases, if I take n to infinity. We just did it. 0, yeah. What about the nth root of n? What does that limit to? 1. What is the x to the 1 over n limit to, provided that x is positive? It also goes to 1. What about x to the power of n when x is less than 1 in its absolute terms? X is a fraction, proper fraction. 0. 1 plus x over n to the n. You know, my dad yelled at me because I didn't answer your question. Yeah. You're complaining about I got a sign error wrong, and you're right. Yeah.
I saw that email.
Yeah. I sent it out to everyone just to show you that, like, yeah, there is a mathematician above me who admonishes me. So what's this? Nope.
0.
Nope.
Oh shit, we ran out of options.
E to the x.
E to the x.
Yes. xn over n factorial. I'll just tell you that that goes to 0. Okay? Oops. I should probably write 0.
Can you explain the e to the x one?
I did explain it. We covered this in class. Right? These are just, I'm reminding you of these limits. Right? Look, I can't remember what the technique was, otherwise I would do it. Right? How did we do it?
Yeah, are you serious?
Bro, you guys have 2 options.
We covered it in class, so we can go back to it. Well, I think if you do some type of, you let L equal the limit, then you use lons to get everything down. And then you run it, and then you'll end up getting an E. Yeah? Well, you just set it up like this, right? Like, so you want the limit of 1 plus x to the n to the n. And then you can take the ln of both sides. I don't know, I forget how to deduce it. I need some time. Well, we did it. We have this limit somehow. We did cover it. I just forget what the trick was. Okay, so let's continue. I guess I'll leave this one for an exercise for you since we're sort of running out of time. So here's an exercise, but the full solution's in the notes. Cn is equal to 2 e to the n plus e to the minus n over e n plus 3 e to the minus n. What is Cn go to?
Don't think it's very healthy. I always feel like I'm explaining it. Or when I'm explaining it to someone else. What is
Okay, so I just need to define some common language so we can talk about sequences. We're actually much more interested in sums than we are in sequences. Right, so just keep that in mind. Okay, so we need to discuss what it means to be bounded and monotonic. Just a couple of words that we're going to need to use so we can all be talking about the same problem. So do you remember what we had these notions of, like functions could be strictly increasing or strictly decreasing? I'm going to write down the definition for this and I'll give you another way of looking at it. So we're going to say this sequence is bounded from above whoops, I skipped a definition. Well, not bounded. Oh, no, bounded from above. Yeah, bounded from above when, okay, there is some number called the upper bound such that every number in the sequence is less than it or equal to. We also have the definition of this for lower bound, to sort of switch everything out. Right? It's sort of intuitive what it should mean to be an upper bound or a lower bound. We also say that an is bounded when it is both bounded from above and below. Below. Oh, mercy. Below. Okay? We can also have many upper bounds, right? One of these upper bounds is going to be the smallest upper bound. And when we find the smallest upper bound, we say the smallest upper bound is called the least upper bound. Okay, so let's see if we can utilize these pieces of notation or this new language. So if I let an equal to n, which is basically the sequence 0, 1, 2, 3, and so on, is this bounded from above? Is there one number which is greater than every number in this sequence? So, no, this is not bounded from above, because it's just climbing all the way to infinity. Is it bounded from below? By what? 0. It also is bounded below by -10 and -1,000 and -1,000,000. Right? It has an infinite amount of lower bounds. 0 is the greatest lower bound, which is the one that we're actually would be interested in. We'd always want the greatest lower bound and the least upper bound. Okay, I'll give you another one. What about this one? Okay, so this is bounded below by 0 and unbounded above. Okay, what about this one? Does it have an upper bound? What does it limit to?
So the upper bound is 1?
And 0 and 0.
Yeah, we can say this is bounded above by 1. It also is very clearly at least 0. Right, that's the smallest it ever gets. So this is also bounded below by 0. Right, so this is a sequence that we're going to call bounded. Right, because all of the terms are trapped in some finite range. Right, so it's bounded above by 1, bounded below by 0, and therefore is bounded. Okay, so now I need to give you a definition for what it means to be monotonic, which is kind of weird. Okay, so AN is called non-decreasing. Okay? And there's a technical definition in my notes for non-decreasing, but I'm going to use a different explanation here, which could be maybe better. AN is called non-decreasing when it is not strictly decreasing. Right, that is to say, we have to have the property that AN is at least as big as the thing that came before it.
So if it's constant, that would be non-decreasing.
Well, let me make sure I got this right. This is non-decreasing. It's not going down when it is, not strictly increasing. Sorry. I knew I got that wrong.
It's not decreasing when it's not decreasing.
Non-decreasing and is less than or equal to AN plus 1. Okay, so basically we need this different piece of language because we're allowed to be equal. Right, so like 1, 1, 1, 1. That's neither increasing nor is it decreasing. Right? So we need a different piece of terminology because all we have is like strict. Right? So something is not decreasing if it never goes down, but it can be stable. Stable is fine. You could be like 1, 1, 1, 2, 2, 2, 3, right? And this is a non-decreasing function because it never goes down. We also have something called non-increasing, which means the function never goes up, but it can remain stable. Right? So it's a little bit different than strictness. Strictness means that you always have to be going up. This is sort of like the opposite version of that.
I thought you said AN isn't a function.
Yeah, but increasing, I mean now by this version. Like the way that you would think of a list increasing,
Okay.
right? Like, remember,
Not like the slope.
we have to be in a mode now. We're talking about a list of numbers, right? That the numbers get to repeat and the numbers go on forever. But we can utilize our like the sort of sensible like English definitions, right? This is what it means to be non-decreasing. Okay. We also have a notion of being monotonic, which is the important thing. So something an is monotonic when it is either non-decreasing or non-increasing. You guys are gonna have to wrap your head around.
Yes, sir.
Yeah.
So it's saying it's either increasing or it's constant when it's not always increasing, but it could be decreasing.
Non-decreasing, never go down.
Yes.
Which means you can be constant or go up.
Yes, it's saying that happens when you're not always increasing, right? That's what it says.
Sorry, I don't understand your
Okay,
question.
so it's saying it's non-decreasing
Yes.
when it's not always increasing. So it could be decreasing.
This is a definition, right? I'm saying this is the definition of non-decreasing. We can't squabble over definitions because they just are, right? But like this makes sense to me. Something is non-decreasing if it never decreases, which means that you can only be equal to the last term or greater than it. Right? That's
I get that, I get that.
yeah.
I know.
So it's not decreasing. In order to decrease, you have to go down. So it's not doing that. Something is, huh?
Why do we need to classify them this way? Like,
But we need ways of talking about this problem, right? Because I can't always say, suppose we have an and bn, which have this property of like never going down. I need to say, suppose we have an, which is non-decreasing. Like today's lesson is basically just trying to expose you to all of the notation ideas and strategies that we're going to need to do all the real stuff on sums, right? Like this is just definitions and stuff. That's what math is like. Anyways, so we have this notion of being monotonic. That means you're either never decreasing or never increasing, right? And when something's monotonic, we have this thing. Well, maybe we should do some examples to clarify things. Okay, so 1, 2, 3, up to n, and so on. What is it? Is it non-decreasing? Is it non-increasing? Is it monotonic? Yeah, this never decreases. That's how you can think about it. So this is non-decreasing. What about this one? A half, 2/3, 3/4, n over n plus 1.
Also non-decreasing.
Non-decreasing, okay? What about this one?
Monotonic.
Oh, monotonic.
Monotonic.
What is it? Either. It could be either.
Well, this is monotonic. This is monotonic.
So all of them are monotonic.
What's this one?
It could be both or neither.
It can't be both and neither.
Or
It can be both or neither.
It can be both.
Well, which one is it? Is this non-decreasing?
Yeah.
Yes.
Is it non-increasing?
Yeah.
Okay.
So they're both.
It's both. So this is both non-increasing and non-increasing. Oh, non-decreasing. What about this one? 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1.
well, it's both, but like at.
No.
It's not both.
Not both.
It's
I'm
neither.
not saying in general. I'm saying like at.
Why is that?
No. We don't have at points. We have a list of numbers, an infinite list of numbers. These aren't graphs. Don't think of these as functions. These are infinite lists of numbers. right? And we can talk about infinite list of numbers having attributes, like increasing or decreasing or being non-increasing or non-decreasing. Like, basically, we can codify all of these things into being monotonic. These sequences will either be monotonic or not, right? This is not monotonic, right? The non-monotonic sequences are problematic, right? Because they're never stabilizing to anything or don't have to stabilize to anything. We're going to have to do stuff here to work with it. So anyways, this is not monotonic. That's how you would say that. Right, monotonic means heading in one direction. These non-increasing and non-decreasing functions are always only going one direction. That's what the mono means. Mono means one. Real means real.
Not that one, that one. It's English. English was the worst subject. Okay, well that's your fault. You'll learn something else. I'm ESL.
I'm writing your exam like over this week,
Oh god.
right? So it would be in your best interest to keep me happy.
What coffee
right?
do you prefer?
Bring it out.
So this is called the monotonic sequence theorem. This is important. You need to know this. You will be tested on this, right? So if an is both bounded and monotonic, okay, let's consider what this means. It means if we draw the sequence, okay, so this is n, it goes on forever. So there's going to be, one dot for every member of our sequence. What does it mean to be bounded?
You have a least upper sum and
Yeah,
least upper bound and a
it doesn't necessarily have to be the least, right? Just get any of them, right? So it just means that I can draw something here. This is the upper bound, right? I can draw something in here called the lower bound. Okay. So are the dots that I drew, can these dots correspond to a monotonic sequence?
No,
No. Okay, great. Why not?
because it's fluctuating up and down.
Because it's neither non-increasing or decreasing. Okay, so let me correct this. If I do something like this, is that monotonic now? Okay, so consider this. Monotonic means you have to be going in only one direction, either up or down. Bounded means that there's a ceiling and a floor.
You're gonna
Right?
approach a value.
Huh?
You're gonna approach a value.
Yeah, precisely. This means that if we have a sequence which is both bounded and monotonic, it has to have a limit. Has to. Right? Because it can only either stabilize or go down. Right? So eventually you're going to hit the greatest lower bound, or equivalently the least upper bound, to get a limit. So if an is both bounded and monotonic, how did I write it in here? Oh, it converges. By which I mean it has a finite limit. Okay, be careful. The opposite isn't true. This is a one-directional argument. Right? If you have a sequence that converges, it's not necessarily the case that that sequence is bounded and monotonic. Right? I can easily give you an example of a sequence, right? Something like this. Oh, maybe I should draw. Yeah, that's better. You see how this is going to stabilize to 0? It's not monotonic. Right? So just because a sequence has a limit doesn't mean it's monotonic and bounded. Well, okay, if it has a limit, it has to be bounded. But it doesn't have to be monotonic. So be careful when you utilize this. It's one direction only, right? Bounded and monotonic implies convergence. Convergence does not imply bounded and monotonicity. Okay, so I know I threw a bunch of new features, terminology, definitions at you today. What I need you to do for Tuesday is to study this. Right? Because we're going to return on Wednesday, and we're going to take all of this stuff and apply it to sums. And it gets way more complicated when we start adding these sequences together. So I need you to be comfortable with the terminology and language by Wednesday, or you're going to be totally lost. And you need to study this anyway. Like the exam is in a few weeks, right? So you might as well start. I think I actually released the Weeby work problems last night, right? So go at least, like skip all the sum ones, but at least try and go do all the sequence ones, because I need you to be comfortable with this by Wednesday, or the class will go worse, right? This last topic is tough, right? Probably tougher than integration, right? Because there's less techniques that I can give you to help. And sums are bizarre, right? Like we're going to learn that 1 plus a half plus a third plus a quarter and so on is divergent. This actually sums to something infinite. Yes. But we're going to learn that 1 squared plus 1/2 squared plus 1/3 squared and so on is convergent. And I'm going to teach you about all of these different types of series and which one of them is converged and which one of them don't. And I'll even be able to give you some equations. Right? We know something along the lines of if we want to sum, what is it? 1 over a to the n. This is 1 over 1 minus a, provided that, oops, the opposite is true actually, as I wrote it. Okay, don't write this down. It may not be accurate. It's usually a disaster when I copy something. Right, but I'm going to give you some of these. This is called a geometric sum, if I remember. But it's mostly the case that we can't find what these sums add to. Right? We can get a computer to sort of try it, but these sums are very difficult and it's super important to science. So please, by Wednesday, be comfortable with this. I gave you about half a dozen pieces of terminology, so at least give the notes a read. Okay. Get out of here. Go enjoy the day.
Lymphatic system.
Yeah.
Are you taking another class?